We spent much of time talking about data warehouse and online analytical processing in this chapter. At the end of the chapter, the book introduced an alternative way to learn concept descriptions. OLAP operation can be seen as one way to learn concept descriptions. Such concept may be, for example, frequent buyers, like that. Through the OLAP process, through different drill down and roll up, slice and dice operations, the user can interactively work with the OLAP system and gather insights about the characteristics of people with different purchasing patterns. So the OLAP processing is can be seen as a user-driven interactive way of identify different concepts and learn the concept description. Alternative way, not using OLAP process, but gathering data from relational table or other sources, and using a different approach can also achieve similar purposes. And this method is called attribute-oriented induction. So how is it different from OLAP? So in many OLAP implementations, it's generalized in a way that the dimensions are holding categorical data. For example, location, date, brand name. So those are categorical data. And measures, the facts, are numerical data. So this the three type of schemas that we have discussed are all designed in this way. So if the user wants to learn concept descriptions, then this inserts a limitation that you cannot flexibly exchange measures with dimensions. You have to just try to make sense of the result that system provides to you. So it's highly user driven, that the user must know the OLAP, the dimensions and measures very well in order to actually create a path using a variety of OLAP operations to reach its goal. So it's heavily dependent on the user's expertise and the knowledge. On the other hand, the attribute-oriented induction is much more flexible. It does not require any schema. All the input to the AOI system is just a table. So it's much more flexible, and also it's data driven. It's more of a data driven. Much of the process of OAI induction is automatic. It's only at the presentation stage, later we're going to talk about that user interaction is possible and allow the user to manipulate the output of AOI systems. So I mentioned, we talked about at this time concept description. I hope that you make a link to the type of mining tasks that we discussed, I think, in the first week of the class. There are two types of mining tasks. One is descriptive, another is predictive. So the concept description is mining the characteristics about a concept or about a class. So one example of concept could be graduate student versus undergraduate student. People not tend to get COVID infected, and people who tend to get COVID infected, for example. So attribute-oriented induction is one method that we can use to perform this descriptive mining. So how OAI is done? So generally, you collect task-relevant data called initial relation using a relational database query. So you have a relational database holding the data that's relevant to the concept that you're going to study, for example, graduate student versus undergraduate student. So you will have the relational database, maybe a university students database. You have students' application information, its course performance over time, its GPAs, and all that, age, hometown and race and all that as your task relevant data. And then you will perform concept generalization by using two methods. One is attribute removal, another is attribute generalization. As you can see, attribute removal, you basically, some attributes or dimensions that's not relevant or very hard to generalize got removed. Or you use attribute generalization, for example, from student's birthday, you can find the age and you can generalize the age to like young, old, mature, and all that. So as you can see, both steps are similar to the concept hierarchy and the roll up step in OLAP, where we either go up, we either remove a dimension or go up along the concept hierarchy. So this says OLAP also performs concept generalization, and OAI does that too. Concept generalization is a key step. That after those attributes being generalized, the patterns becomes a little bit clearer for us, for the users to derive the general characteristic of certain concepts or compare different concepts along a set of generalized attributes. So lastly, with those generalized relations, the user can interact with the system to do presentation of to manipulate the presentation of the result so that the comparison becomes more easier to identify. Here is one example that in a university database, we can try to generalize some attributes to find the general characteristics of graduate student. So step one, we fetch relevant set of data using SQL statement, assuming this university has all the information related to student in one table, which is commonly not possible. You will have to select from multiple tables using a whole set of join statements, join on student ID, so that you can actually gather all the information from different tables. Such information may include name, gender, major, birthplace, birth date, residence, phone number, GPA, etc., etc. Even including student groups participated, whatever the information that university collect of a student can be. And then because we are going to study the general characteristic of graduate student, we have a condition here, student status is in Master of Science, MBA, in PhD, or any other labels that indicates a student is a graduate student. So that's the step one. We gathered useful information. This information is going to be most likely represented in a large table. Step two, the algorithms start to perform attribute-oriented induction. This is the step that the attributes becomes generalized. In the next slides, we're going to actually look at those generalization steps. Step three is to present the result for the user to see the general characteristics. The presentation part is where the user can start to interact with the system. The user might want the system to draw a pie chart, to draw a contingency table, to use any other visualization tools to bring out the key insights. So in this example, we have the initial relation that we collected using the select statement. We have name, gender, major, birthplace, birth date, residence, phone number, GPA collected. And the system will start to generalize. Okay, so looking at the first column, name, the system will see, oh, this column has very high cardinality. And for categorical, the system going to have a set of generalization rules. It look at a column and see if these columns match the rules the system has. The system may have rules that says categorical data with less than 50 cardinality perform this generalization. And so the algorithm checked this one and see this one does not match any generalization rules. Therefore, the system going to remove this. So this column going to be removed from further consideration. The system look at the second column, gender, and the system see there's two distinct values. So the systems can find a generalization rule. It says when you have less than categorical data less than 50 cardinalities, keep them or generalize them. In this case, you might have a more specific rule that says the system that the column with less than 8 cardinalities, simply keep them. There's no need to further generalize them. They're generalized already at the right level already. So therefore, we can return it. Just return the original value. And then we look at major. We count it and we see, okay, there is a rule says how to categorize the majors. So look at this CS physics. Those two examples might be generalized to science. I would think so. If you have like civil engineer, electronic engineer, those majors going to be generalized in engineer. Or you have other business management, MBAs, is going to be generalized in business category. So for every column, the system is going to check for the cardinality and check to see if there is a generalization rule. If there is, the system is going to apply generalization, or if the value, the cardinality is just too great, the system is just going to remove them. And for GPA, for example, numerical values, the system might decide to discretize it into very good, excellent. So those rules, after it's being applied, you will get a generalized relation that looks like this. So after name is removed, we have two gender, we have major being moved up to a more general level. We have birth place. We probably have well, from streets to city to country, and the system says to generalize to country. So we can now our generalized it becomes Canadian, US, and all the rest goes to foreign. And once this relations is generalized, then we can have the the user can interact with the system and have those generalized relation presented in different ways. In this example, we have a cross table to show the distribution of gender across different countries. So then you can, obviously, with a table like this, you want to perform a chi-square analysis, right, to see if there's correlation. So I think I have described everything that's listed here. Oh, yes, here. So the removal part we have described already, but to recount, if there's no generalization operator on an attribute, remove it. If A has a large set of distinct value and it has no way to generalize it, or its higher level concepts are already being expressed in some other attributes. For example, age. The birthday we can generalize, but if there's already a age group range, then we just remove this and plug in age range. An attribute generalization if the distinct value or cardinality for an attribute is large, but there exists a generalization rule on A, then we can use that rule to generalize A, like what we have did here, GPA being discretized, here major being generalized from CS physics to science or other groups, depending on the input. Attribute threshold control, we want in the end for each attribute to have a cardinality of between 2 to 8. So gender is one example, it has 2 distinct values. Some other places, maybe majors, ends up with 8 different major disciplines. So typically it's between 2 to 8. That's at this level of generalization, it often becomes easier for humans to identify the major characteristic for a concept. For example, in this case, graduate students. Generalized relation threshold control. There is another control that it can be user specified or a default value being used. Similarly here, user can specify or using a default value. This says how many relations, how many attributes going to be kept, and each relations could have how many different values. So the presentation part, as we mentioned earlier, this is the part of the vast majority of those attribute removal and generalization are basically data driven, based on what data is there and what generalization operators or the rules has been defined. You have the system automatically process those and decide how to generalize and how to remove. Then at the presentation stage, the user has start to interact with the system and have different ways to represent the result. So we have mentioned, we have showed generalized relation. So the things can be presented in this way for the user to see if that makes sense to the user, or it can be presented in many other ways. The cross tables that we saw earlier, by bar charts, pie charts, whatever visualization techniques that can be used. The user can also map those results into rules like association rules. To just extend the concept description learning through AOI, we can easily imagine the methodology can be extended to mine class comparisons. So this is also one type of concept description mining task. So the goal is to compare two or more classes. And so the method slightly changed from the previous one. When we collect the relevant data, we will partition the data based on the classes. So in this case, if we want to compare graduate students and undergraduate student, we will have one table for graduate student, another table for undergraduate student. Then we will generalize both tables to the same high-level concept. So the generalization step is going to be consistent, the same generalization applications being applied on both tables. And then we can compare the results and see how the after the attributes being generalized, what are the distributions. For example, we can probably find undergraduate students are generally younger than graduate student, and younger student, undergraduate students are generally have lower GPAs than graduate students. And then we can present those present for each tuple its description and the two measures. And the two measure, one is support, the other is comparison. The support describes how the data is distributed within this class, so within undergraduate, and the comparison is the distribution between class. For example, we can have in one of the tuple, undergraduate student tuple may have a GPA that's fair, and we can indicate what percentage of the fair grade GPA is within this undergraduate class. And we can have other percentage of count for the other class as a comparison. So even better, we could have those tuples in terms of presentation to the end user. We can highlight the tuples with the strongest discriminant features. For example, if we have if the data shows that the percentage of the fair GPAs and the percentage of the excellent GPAs between undergraduate and graduate student are very, the difference is large, are very different, and we can highlight that tuple, those tuples, the fair and the excellent tuples within the undergraduate and graduate generalized tables. And we can perform additional given the data here when we have the earlier we show that the data can be presented in those variety formats, for example, contingency tables that's suitable to conduct correlation analysis using chi-square or using other correlation analysis for numerical data to find best to distinguish characteristics that and different classes. So the key concept here when we mine class comparisons, this the COI, the OAI part, the concept generalization has to be done synchronously, so that the generalization performed on both classes are the same. This makes possible in the end for us to compare those two classes. This can be extended to more than two classes as well. So to summarize the AOI approach to concept description versus the cube-based OLAP description, my feeling is that OLAP was designed for database data business intelligence, and it's defined in a very defined in a standard way to separate dimensions and measures. So there are some limitations. It's not as flexible as concept description for the concept description task. Although they do share lots of similarity, they share similarity in data generalization, so attributes being generalized. And we can present data summarization at multiple levels of abstraction. And AOI systems also supports interactive drilling, pivoting, slicing, and dicing. So those are the similarities. The differences, OLAP has database support. It can drill down to very low level to the regional data, which AOI is less so. I think those are more of a design choice. OAI analyze the data to generalize different dimensions, performing different generalization rules, making the technique more flexible in handling different types of attributes. And OAI also works on data which are not in relational forms. So any data that you can actually be presented in a tabular format, AOI can work on those. That's the end of chapter 4. To summarize, we have discussed a whole suite of basic concepts related to data warehouse and OLAP operations. We talked about the basic concepts, excuse me. We talked about the data warehouse architecture, multi-tiered architecture, 4 levels, design and usage. We talked about some implementation elements. We did not cover the entirety. Obviously, we only have in 1 chapter on this. You will need a book to cover the entire all aspects, but we picked some key elements to help us to understand the data warehouse and data cube and OLAP operations. Lastly, as a contracting technique, we introduced attribute-oriented induction for concept description and class comparison. I would remind you to check the learning objectives and make sure that those steps covered are clearly understood. Post your questions if you have any. Thank you very much. That's the end of chapter 4.